So there will be like 3 or 2 topics today, but very short. I'll make it very short. And the first topic I'm going to mention is basic inference instead of MLE and MAP. Let's just quickly recap what we did last time. So still the same problem. If we have collect some data and we want to predict what's the probability of this new x, first we need to build a distribution, and then with the distribution we can calculate the probability of x. One way to build distribution is to estimate the parameter theta using maximum likelihood. This is equal to max theta p. D is like a few data collected before, and they are independent. And the MLE estimation is maximize this function and get the theta. And this method has a problem of overfitting, so we use the MAP, which is the posterior probability of theta given b. Again, this though has a regularization of the theta, but still is a point estimate, which can still have similar problem of MLE. So to solve this problem, instead of point estimation, we average over all the possible theta in the model to solve this problem. So another thing is to predict the probability of x, given estimated parameter, we can, for example, we have this x. We are going to compute the probability of x given theta, either MLE or MAP. This is the theta. But in general, what we are going to estimate is the probability of x given data d. But here we use theta instead of d because theta is estimated from the data d. In basic method, we are not going to do this. We are going to do this. This px given d is equal to px theta. Theta is the parameter of distribution given d. Theta. This is just marginalized all possible parameters of theta. This is equal to px given theta d times p theta given d theta. This is just the base rule. This we can recognize this. This is a posterior distribution of theta given d, which we computed last lecture. And this one, because given theta, x is independent of d, so this can be simplified as px given theta times p theta given d. In our last example, we used the Bernoulli distribution. In this example, we are going to continue that estimation. This x given theta, well, we are going to x equals to 1. In Bernoulli distribution, if you get a y, the probability of getting a y is actually the parameter theta. The Bernoulli distribution is px given theta goes to theta x or 1 minus theta 1 minus x. Yeah. So if we want to get, if this is equal to 1, the probability that's equal to 1 is actually equal to theta. So So this term can be simplified as theta times the post. Well, given this is the Bernoulli distribution, is it? And this term, as we remember last time, this term we use Bernoulli distribution and times this counter prior. So the definition of counter prior is if you use that distribution to times the likelihood function, you will get the posterior function back in the same form. As we computed last time, this term is equal to beta distribution. Theta, given the parameter A and B. A here is the original A in probability distribution times the observation number of observation of heads you have, and the B plus, let's say, n0. That's the number of tails we have. And look at this. This is actually the expectation of theta given D of this distribution. So this is E of theta given D. Well, the expectation of this beta distribution is is A minus total number of observation. So this is the basis estimate of theta. So this method, as we mentioned, average over all possible parameters. So it's not dependent on any particular parameter. So it can avoid the problem of say overfitting, because this is not point estimation. In terms of, well, you can do the same derivation for lots of exponential parameter distributions. So, and you can.
Excuse me, why you put relative exponent theta exchange in theta?
This one? Because this is actually when the x equals to 1. For the Bernoulli distribution.
Okay. Only for x equal to 1 you.
Yeah. This is like short topic, so I put it in the front. So
the last time the solution is what? I forgot. So what's when you do map estimation, what's the theta there?
the theta there, I think
it's not the same.
the same.
In
Yes,
this case.
theta is the same.
Okay.
But the theta, the estimate theta is going to plug in.
But I think it has
Yeah.
some +1 or -1.
Yeah, maybe is that like
I think in the top it has -1 and in the bottom -2.
maybe yeah.
Oh, yeah.
And,
The last one we had.
I think so. Because -1 and
Yeah,
the
that's
bottom
what
is the same.
I think here -2, -1.
Mm-hmm.
The code, source coding, do you derive or you have something?
No, actually, I think no, we don't.
Let's go back to the main topic, which is not going to be 12. Last time we talked about the exponential family, which is in the form of x to is equal to turns out for the maximum likelihood, the exponential family has some nice properties. So because this the distribution we derived last time, Bernoulli or Gaussian or lot of distributions, they are exponential family. So for all these distributions, it turns out you can use maximum likelihood to get the closed form solution. So this time we just derive the maximum likelihood for this formula and see what we can get. What's common in all these distributions for maximum likelihood. So again, our setting is we have a data set D, which contains a few points, and these data are IID. Which is very important constraint. To derive the maximum likelihood, first we need to write the likelihood function, which is P E given beta. This is equal to P x1, x2, xn. Because these data are IID, which means they are independent given beta, so we can write this into this form. And this is the very important assumption of the data, and a lot of algorithms are actually based on this assumption. If this assumption is not met, we cannot decompose this joint distribution, joint probability into this form. And in many cases, actually, they are not independent. For example, if you measure temperature of an area, because they are related somehow. If they are geometrically closer, they have some correlation. So in that case, you cannot use this ID assumption at all. So this can be written as multiplication of xn with beta. And this is equal to, let's substitute this p into here. This is equal to n and well, for the convenience of computation, we assume there is a z, which is equal to z of beta, 1 over z of beta, which is equal to g of beta. This is just different form of writing this distribution, that equivalent. So you have this multiplication of this z beta times hxn and times exponent beta transpose sufficient this Sn. Again, we take the log. We write down a log likelihood of this beta, which is equal to this. In this form, we take log.
What you said that was the z to beta?
Oh, this part?
Yeah.
I just switched I just introduced a function which is equal to
Just
yeah, that is equal. Yeah, just follow the calculation. It's easier. Because this term does not depend on n, so we can just write down as beta. And this term, yes, it depends on x, so we write like this. And times exp. Because this multiplication, I can move the multiplication into here as a summation. So it's beta t times summation of x or s x n.
I was late for the question. Previously, you have x and d was the difference x and d.
X what?
Previously, x and d,
X and
x and d was the difference between x and d. Not here, actually. The previous.
x and d.
D is the difference.
Yeah, yeah.
Was x.
Oh, x and d. There are multiple x and d, which
Yeah, I guess this is too late for the
okay.
so we wait.
And here the setting is the same.
But okay,
I think you write something
you
is
want
given
x,
d.
yeah, you want x given
Oh,
the,
Oh, x given d.
yeah.
X given d.
So what's the difference between
Sorry. This is the like data you already know before. This is the new x.
Oh, okay.
You always want to. This is called predictive distribution. So you always want to know something. You have a new x. What's it? And yeah. This is just like I observe this, and if I say something new, what's the probability?
You wrote, okay. So, there are couples you wrote, like, you said I expected to do like theta given d, and then you compare it like theta given x. I guess you need to write down there. I need to see that first. Okay, the difference between math and basic.
Oh, okay.
What that?
I think the map here is from you estimate a particular theta. This is just single
So
value.
this is much more likely.
Or map. Because both MLE and map are trying to estimate the single value theta.
Okay. But you do a white maximum likelihood, yeah. I mean, your white maximum likelihood.
Oh, here, if you have a new for Bernoulli, you have
But then like also x you said is the future, right? How can it? I mean, it doesn't sound. Isn't that you should read from the data, both of the values are unknown here. So what was the? Yeah, because you said x is the future, right? Yeah.
Okay.
X is the future, right?
Yes. And this theta, because you have observed the d before, you have d here.
Yeah.
From d, you estimate the theta.
Yeah, that makes sense. I mean, when you want to have p theta given d, yeah,
P theta given d.
yeah, that's what you say basic. That's what you call it.
Oh, P theta given d. This is the ambient here. If you have marks, see.
Oh, okay. Then how to write down the basin?
Oh, the basin is essentially we are trying to estimate this. We have the known data d. We want to estimate x, which is new.
So you mean it doesn't estimate the count, it just estimates the picture values?
It estimates, but this can be written as px theta or d integrate over theta.
Yeah, that part I agree. But, I mean, can you write down the what you roll down pieces that you raise. You roll down.
You can use all of the words.
This is equal to.
That's just like the comparison. Your ML and the Mac and then the basic.
Oh, okay.
You say this is the basic.
This is the basic.
Okay.
Because
And then you say the map, you roll what? You roll P theta given X?
Okay. This is computing the predictive distribution. And but for the map, but again, the map is for estimating this, not for predicting.
But that doesn't make sense, right? Your xi you say is like future, you don't know. And like, yeah. Because x you are not observing x, right? You say x is like a future.
Yeah, but if you want, well, should I say predicting? But the predicting here means, well, yeah, predicting here means you have a given x, but what's the probability you can call it?
I don't know. It doesn't seem to have any difference. I mean, the difference here is more like when you want px differently, you are predicting the next, not estimating the parameter, but estimating the future, right? But the other one is that you are estimating the parameters. It doesn't sound like really there's a difference.
Well, then for this x, what do you think this x is?
Future, right? That's what you say.
In this context, these two x are the same.
But then if that one is also future, yeah, that's nothing you can use as ground basis for you to do an estimation. Like you don't know theta, you also don't know x. And when you write down this, what's the point of that?
Yeah, I mean here, well, if you want to compute this, you need to estimate theta first. If you want to estimate theta, you need to have data. When you have data, you can use MLE or MAP to estimate the theta. When you have theta, then you can plug in any x.
Okay, I see. So you mean like this factor you are supposed to be known in this case?
Yeah. If you want to build, yes. You need to know. So there are actually two steps. One is estimate parameter. One is compute the predictive for probability.
Okay, it sounds fair enough.
It's important here to how to find the theta. For example, from MAP or
This one?
MAP. Yeah.
Do you see that? Because this setup here, at the very beginning, you have observation of these. You have model observation. You already have the so-called training data. You want to fix, if you want to estimate theta, there are two ways. MLE, which is equal to R max P D, which means you need to figure out theta parameter, which is most likely to have generated D. Another way is exactly the same, but MAP is equal to theta. You want to maximize this instead of this. There are two ways of estimating this.
When here it's important which one you select for this theta and after that doing base estimation for the x is the predictive estimation. Is it important?
Which way to choose?
Yeah.
Yes. MLE has a problem of overfitting. If your data is not really enough, you can have a very biased estimation, which makes sense if you use this parameter. If you use this method, for example, the flip coins. If you only have 3 data, which all heads, well, yeah, it's bad luck. Then if you have, then this theta in the context of parameter distribution, the theta is going to be 1. If you plug in 1 into the parameter distribution, whenever you predict tails, it's all going to be 0. There's no chance of getting a tail because all your 3 data are heads. So your estimation of parameters fits the data only. Then consider the consistency. In MAP, you need to add your prior knowledge into the estimation. Then actually there's the dispute about the prior. And so which prior is good prior? So someone call this type of prior called subjective prior. So it's you who specify the parameter of the prior. So that's your personal view of the prior, which is not necessarily correct. So I mean there are different problems of different methods. That's reason. Oh. And yeah. This is the product of this requirement likelihood function. No, this is a joint likelihood, a joint probability. And if we are now we are going to take log of this product to get log likelihood of eta. And to take the log, so we have n log plus. Now, if you take a log, so this product becomes the summation. So we have a sum hx times again plus log act on this exponent, you get cancel out. So we have beta times summation of x. This is the log likelihood. This log likelihood can look like something maybe on this or something. If you want to get this is unconstrained optimization problem. So you just take derivative or gradient of this function. You can get this critical points. And now we take the gradient of this function. Because the gradient is just a vector whose components are partial derivative of each component of the eta. So we just for now we just take partial derivative of one eta here. And this and partial derivative of eta. J's component is equal to
button.
So we are going to compute this. Why we want to compute this? Because for the unconstrained optimization problem, if it's single variable, you take the derivative. Yeah, if they have multiple variant, you take the gradient and set to 0. So we are going to compute this and set it to 0 and see what we can get done. And this gradient is just equal to partial derivative of black component, non-black component of the first component, and then the second component, and nth component. This is the gradient of this guy. So we just pick up a component to compute. So the rest is the same. Okay.
Yeah.
And so, let's see. Just move this. They're the same.
So where's the G actor? What's the G actor?
Just replace with
You said that you.
out.
It's a function to make the probability because
Yeah, but then like why you said like it become disappear
Oh,
now?
come this one.
yeah, exchange with 1 over z.
Just,
Where's it?
But then it depends on actor, right? Okay, where's oh, okay, theater is there, okay.
It's red. It's
Yeah, I need to pick glasses.
So here we just compute the partial derivative with respect to a certain component. Then we get there's minus sign. That's why take the y over stuff out of the log. And then we have minus n times c beta over 1. And then upper derivative of c beta j and plus because this term is a linear combination. This is inner product of this guy. So if you take partial derivative of one component of beta, so only the corresponding term remains, which is equal to x. And because this term does not depend on beta, so it's not 0.
y against sigma. Y is against sigma. Because 1 component.
Which part?
The last part.
Last part?
Yeah, only SJ is. Why is sigma before that? Why you do summation?
Well, yeah, I think you're right. Let me see. Oh yeah, actually this term is equal to beta 1 times this. 1 times plus this one times this. So if we take partial derivative of say beta 2, we got this term back. And because this S solution settings is also a vector, this eta transform eta is like this. So it's eta 1 equal to this is the summation of x1 summation x2. So the inner product is it's just like this. And then we take partial derivative of beta 2. This term is 0 because it has no beta 2. And this term beta 2 take derivative, it becomes 1 times this. And this is the interesting part. And Right now, let's see what's z eta. And z eta, if we go back to this form, z eta times this whole thing. Well, the integral of the whole part should be equal to 1 because probability. So if we move, well, this is equal to 1 if we integrate. So this integrate dx first is the variable. If you move this out and put it to this side, so you can get integrate this whole thing is equal to z.
Why you put it equal to 1?
Oh, because this is probability.
No.
Oh, this is a PDF, so you integrate PDF,
Then
then you need to be 1. So eta is equal to integrate all this term. So yeah, let's compute what's this now. And eta z. And when we take this derivative, we can act this derivative. Well, assuming this is nice form, we can take this derivative into this integral. Then we can get hx, exp, everything the same, times the same thing. S J X. And notice we have this term here. So if I move this term inside of this integral, we get z eta hx exp times sj dx. And this term here is just the exponential family, the probability, the form of probability. It's just this one. Then we get p x beta x dx. Yeah, the whole term is equal to this one, which is equal to the expectation of Sx. This value times its probability, so it's the expectation. If we substitute this part back to here and set to 0, we have 0 is equal to minus n times the expectation of sufficient statistics times this value, and equal to 0. If we move this term into the left side and then divide n, then we have Sx is equal to n Sx. We get this solution. This is basically saying the expectation of sufficient statistics of x is equal to the sample mean of the sufficient statistics.
exactly is.
Oh, for if it for each distribution, for Bernoulli, for Gaussian, if you transform the distribution into the exponential boundary form, you can get corresponding x. Each distribution has different x.
Yeah, in the exponential.
Yeah, in the exponential boundary. And what's the use of this result? We can use this result to quickly find out the expectation and the maximum likelihood of the distribution, exponential distribution. Let's give an example. Is there any question? Doesn't make sense. So there are two. There are two results we are going to leverage in the following application. So, in this tool, the last time I used this tool.
Okay, it doesn't.
So there are two results we are going to get from this derivation. One result is ln z beta is equal to expectation of sufficient statistics. This is one result. Another result we get is the expectation of the sufficient statistics. It's equal to sample mean of the sufficient statistics. And now we have these two results here for the exponential family. Let's see an example how we use it. We just pick up a simple distribution, like exponential distribution, which is equal to px lambda. So this distribution is also a member of this exponential family. If we match this to the exponential family distribution, we can get a few parameters. The z is equal to this, and right. Actually, x equals to 9, and the beta. Actually the sx is like you said, it's minus x. Yeah, it's just lambda. So here we have this result. Let's plug this in. Ln the derivative of ln of this guy should be equal to the expectation of sufficient statistics, which is equal to b ln. Let's compute this first. B lambda is equal to this guy. This guy. And this side, sx, is equal to b, because sx is equal to minus x. So b minus x is equal to minus ex. So because these two, according to this, these two should be equal. So minus lambda 1 is equal to minus x. Yeah, so the expectation of x in this distribution should be equal to or 1 over lambda, which is prime. And another example, another application of this is we can get a maximum likelihood estimation purely from these two results. Let's see. Let's compute, because we have to compute this term. This term is somewhere here, right? And right now we need to compute this term. And this term is equal to n over summation, which is minus x, is equal to this guy, which is equal to minus n xn. If we set this to and now we have the expectation of x is equal to 1 over lambda. So this term is equal to this, which is equal to minus 1 over lambda. And these two should be equal, minus 1 over lambda. These two are equal. So we cancel all this guy and flip this guy, and lambda is equal to n xn. This is maximum likelihood estimation of lambda. This lambda is equal to this guy. There should be more application of this. At least I see in the expect EM algorithm. I think they leverage some result from this derivation. I think that's it. Deriving this is really boring, but when you see